Hi, AP Calculus. This is lesson 2 from section 1.2 from the textbook. I'm going to be talking today about some more function operations, function compositions, and a few word problems as well. So the first example I want to show you guys is number 32. 32 is asking us to do a whole bunch of things. It's asking us to find not the composite functions, but just the operations of adding two functions together, subtracting, multiplying, and dividing it, and then finding their domains. I'm only going to do one example of this, and we're going to look at 32. So the first thing I'm going to do is talk about adding and subtracting. So the two functions are root 3 minus 2x and root x plus 4. Now right off the bat, you'll find pretty quick that the actual composite function itself is not a difficult task. You put a plus between two roots, you can only actually combine what's inside the roots. Actually, you can't combine what's inside the roots ever. All you can do is say, hey, I've got 3 root 7 plus 5 root 7. Since they have the same root, you can call that 8 root 7. But unless they have identical, I think it's called the radicand, the thing inside the radical expression. Unless those two things are identical, you can't combine the outside. So this is what it is. Ta-da! So then if it's subtraction, you just put a minus in between them. Yes, it is that easy. And here's what you do beyond that. To find the domain of these two functions, you have to take into account the fact that any even root has to be greater than or equal to 0. So 3 minus 2x is greater than or equal to 0, and at the same time x plus 4 has to be greater than or equal to 0. So if we subtract 3 from both sides, divide by -2, this flips and becomes less than or equal to 1.5 or 3/2. And then over here, simple subtraction of -4, and you get x must be greater than or equal to -4. Now, to put this in context, I need a little more room here. To put this in context, we're looking for the shared space that both of these functions occupy. So this is its domain. It's where the x values live for this particular part of the function. Same thing here. If I were to graph those two just to get a quick visual of what's going on, x is less than or equal to 3/2 is going to be looking like this. X is greater than or equal to -4 looks like this. So its combined domain needs to be only what both parts share. So both parts of the function live right in between here. And that's going to be our domain. Our domain is going to be from -4 to 1.5 or 3/2. Or you could write it as -4 is less than or equal to x, which is less than or equal to 3/2. So there's our domain for f plus g. And it happens to be the exact same domain for f minus g. F minus g is basically, well, you saw it earlier in the video. This, and then the domain, same as f plus g. And I'll just leave it like that. If we come over here, we're going to look at the multiplication and division of those. So when multiplying, let's make sure we get the whole thing. When multiplying, you can multiply non-identical radicands. So like a quick example of that would be if you had 3 root 5 times 4 root 8, you'd multiply the outside quantities to get 12, and then the inside quantities to get 40. All right, now that requires some simplification if that's what you're going for, but I think you guys get it. So this can be one radical where they're being multiplied together. However, I don't want to multiply that out. I don't want to expand this expression because looking ahead, I recognize that it's going to be a quadratic. It's going to be x squared, some quantity like that. And it's also going to be compared with an inequality to 0, like that. It'd be like a polynomial on the left side must be greater than or equal to 0. Well, when you're trying to determine where that what the solution is to an inequality like that, you ultimately have to find the zeros of the polynomial, use those critical numbers, and then test intervals. All right. So if I'm not making a whole lot of sense with just, jibber-jabbering about this, basically this is the format that we want. We don't want to make it more complicated. So from here, you ask yourself, where does this equal 0? Where does 3 minus 2x equal? Okay. I wrote that terribly. 3 minus 2x, where does it equal 0? And where does x plus 4 equal 0? And we already figured that out over here. This is negative. This is 3 halves, and this is negative 4. So we set up our intervals from negative infinity to negative 4 to 3 halves, and then 3 halves to infinity to kind of test things out and see where this function lives. We're going to use brackets because of the greater than or equal to. You pick a point in between, and then you are plugging into this inequality to see if it's positive or negative. All right, if it's positive, it satisfies the condition that we need to be bigger than or equal to 0. If it's negative, it does not satisfy that condition. So test 0. 3 minus 2 times 0, that'd be 3, times 0 plus 4, so 3 times 4, that's a positive 12, which is greater than or equal to 0. If you test these two in that same fashion, they fail, and that's our domain. Okay, so if you do the f divided by g, it's actually a very similar situation to what you see over there, except it's in fraction form. So let's go to this side, make some room. F over g is root 3 minus 2x divided by root x plus 4. Now you can use the rule that if you have a root on the top divided by a root on the bottom, both square, you can simplify that and make it a big fraction inside of the root. And the only reason why I think that's helpful is because we just talked about how to solve rational inequalities as they're compared to 0 like this. And what we did was we said, find the critical numbers from the top. Since it's equal to, it's bracketed. Find the critical numbers on the bottom. It's a parenthesis because it's a domain issue on the bottom. You can't divide by 0. That makes the bottom 0, so I can't include it. And then you set up your intervals. So almost identical intervals to what we had before. Testing the same points. Look, and I'm still gonna get positive for 0 because instead of 3 times 4 like you had over there, it's gonna be 3 divided by 4, which is still positive, which is still greater than or equal to 0. So this would be our domain for f minus g, and testing these two also yields results that are negative and they don't work at all. All right, that was a very intense example, but we're through it. Let's now talk more about composite functions, g of f of g, all that good stuff. Number 37. Wrong computer. All right, 37 gives us f of x. Actually, you know what? I'm doing number 39 first. That's a simpler move than this one. Let's go to 39. 39 gives us these two functions, f of x and g of x. They're asking us to determine what f of g of x is, find its domain, and then do the reversal of this. So keep in mind that this is just a replacement of the g of x function moving into the x values of the f of x function. So f of x is going to be root 25 minus, and it used to be x squared, but now it's g of x squared. That's what it means to be a composite function. So that looks like 25 minus the square root of x minus 3 squared. Now when you square a square root, you get 25 minus, keep the grouping symbols, x minus 3, and that gives us 25 minus x plus 3, which ends up being 28 minus x. Okay, just for the domain on that, you got to take into consideration two parts. The first part is the domain of what you see in front of you. So the inside of the root has to be greater than or equal to 0 because it's an even root. Subtract the 28 from both sides, divide by -1, you get x is less than or equal to 28. But there's also the input function's domain must be taken into consideration. It must be taken into consideration. It's like a pre-existing condition that doesn't change when it's inputted into the new function. So what's our pre-existing condition? Our pre-existing condition for g of x was that x minus 3 must be greater than or equal to 0. Okay, so even though x can be less than or equal to 28 for this algebraic expression, it also must be bigger than 3. Giving you that domain for part A. Part B looks very similar, except we reverse the roles. G of f of x looks like this, which means I'm taking my g, which was root x minus 3, and plugging in f of x for the x. Keeping in mind that the pre-existing condition for root 25 minus x squared must come into play. So the f of x function is root 25 minus x squared inside the parentheses. Keep in mind that this right here is the equation for a semicircle of radius 5 centered around the origin. The domain of this thing from -5 to 5. So that's our pre-existing condition. The second part is I can't really do much with this function. I have to set the inside of the total root greater than or equal to 0. And I'm going to do that on the next video because I'm running out of time.